So as we saw, like in yesterday, some of the slides, and also if you see, like these days we are getting into these modern clusters. I introduced like there are basically 3 ingredients: and the multi-core technology, the InfiniBand technology, and also the accelerators, both GP, GPUs, and mic. So these are all the commodity clusters, and you see all these large-scale systems are using these components. And if you take a look at the parallel programming models from the top, how people try to program, of course, the MPI is the common one, which is the distributed memory model. But the shared memory model, which is the cache-coherent shared memory model, it has not scaled to a very large-scale systems. So the next generation thing, which is coming up, is the partition global address space model, all called PGAS. It has different kinds of flavors, and not only like the PGAS models, but also the hybrid MPI and PGAS models. Those are becoming important. So in my group, for almost like the last 20 years, I mean, we have been trying to see how to design these kind of programming models for multi-petaflop systems and exaflop systems, and what are the kind of research challenges. And if you take a look at the lower level, these are like we have the multi-core, many-core architectures, the networking technologies and accelerators, and the top we have of course the applications, kernels, and applications. So we need to take advantage of all the features here and try to deliver the performance to the end users so that they can really run their science applications. So in between, then we have those things like the typical applications run over the middleware run over the programming models, and then this is where in my research group we have been working very old days, starting from Mirinet, Quadrix, InfiniBand, even the 3D like the wormhole routed systems in the very old days like IBM SP1, SP2. So continuously we have been working on this aspect of the communication library and runtime and programming systems. And as the systems are becoming more complex, we are also exploring a lot of co-design opportunities across these different layers to deliver the best performance, scalability, and fault tolerance. So we keep this as like a very broad goal because the programming models are changing. We call it like MPI plus X. X can be anything like any of the PGAS models, or even a very simple OpenMP, MPI OpenMP code, or you can think of like a MPI and CUDA, or in general MPI plus PGAS. So we have within the group, like these are all our like the challenges we try to solve, like scalability for million to billion processes. How do we efficiently support internode and internode communication with extremely minimum memory footprint? How do we support hybrid programming? And as the number of cores per node are increasing, how do we balance the communication within the node versus the across the node, and support for multi-threading? And there are a lot of issues on the collective communication, taking advantage of the new offload mechanism, non-blocking collectives, which is the MPI3 standard, topology aware and power aware. MPI3 also has the RMA model. And then, of course, the support for the GP, GPU accelerators, fault tolerance, and QoS, and also the very recently also the virtualization is coming into action. So in that context, I mean, we started this project, as many of you know, and also like Dan gave some broad overview of how this stack was being used in the older days. We started almost the day one of InfiniBand in the year 2000, 2001. The first MVAPICH, which was the MPI1, was introduced in 2002 at the SCO02. And then over the years, we have changed it to, enhanced it to like to support the MPI 2.2 and the very latest MPI 3. Also, we have extended it to support for iWarp as well as for the Rocky. And as of like this month, we are almost like being used by more than 2,200 organizations in 73 countries. So this shows like a little bit of timeline of the project. If you have not seen the slide, so we started with this MVAPICH. Then together with the MVAPICH, we also started this Osu Micro Benchmark suite, which a lot of people use all over the world now to evaluate the performance of different API calls. And then we started the MVAPICH 2 project. And then at that time, I think a lot of users had moved to MVAPICH 2, so we declared the end of life for the MVAPICH, which was supporting MPI 1. So now this is the main software stack, which supports both MPI 2 as well as MPI 3. And then MVAPICH 2X, which supports the PGAS functionality. And then very recently, which is the focusing on the GPU Direct Rdma, the technology from NVIDIA. So those are the kind of things. MVAPICH to mic is not yet out. It will be out very soon. It is being used in some places. I'll talk a little bit about that. But in a few weeks, you will be seeing also the MVAPICH to mic. So this shows like a just a trend. This data is from our website. How the downloads are happening. So we almost crossed like they said 222,000 this last month, and is also available with a lot of different stacks of many different InfiniBand vendors, Ethernet vendors, as well as server vendors, and also empowering a lot of these systems. Dan indicated. So the largest system is the Stampede. So all those users he mentioned, like 5,000 users and all, they are being directly benefited on a day-to-day basis from only one system. So like this in all other systems like this, Tokyo Tech, NASA Playdesk, and a lot of other systems, people are trying to benefit from the MVAPICH stack. So whenever we make the release, I mean, of course, our primary goal is the research. So whenever we want to actually explore some new designs, they are first presented at the conference and journal publications. So that's what we do first. We explore different designs, and then we take the best performing design and then incorporate that into the code base, and we go through a very rigorous QA procedure and testing. We have exhaustive unit testing, a lot of different test procedures, performance tuning, application-based evaluations, also the evaluation on large-scale systems. And those of you who are not here for the tutorial, I indicated we have almost like 60 servers continuously doing 24/7 QA testing. So we have developed capabilities like if we introduce a patch, in 36 hours, we should be able to find out the answer, like it is a stable patch or a stable feature which is going. And then we go through a lot of regressions and a lot of in-house tools to make sure like where the errors occurred in our testing and how to fix it, performance regression. So all these in-house tools we have developed which help us to push out these releases in a much more stable manner, at the same time delivering the best performance. So even when we make this release like alpha beta versions, there could be some corner cases, but we try to handle most of these. So you people should be welcome to actually even use alpha and beta versions for application studies kind of thing. So this shows the overall the MVAPICH to stack. So we have like mostly the CS3. This is where the InfiniBand interface lies, and then we have the different kind of IWAR, Rocky, the QLogic/Intel, now the PSM. We have the standard TCP/IP, and then the shared memory, and we also have the Nemesis interface. So currently, all the features and the maximum performance is available here. And yesterday there was a question, so we also support Nemesis, and then we are trying to unify these two so that all the features can be used by both these interfaces. Now this shows the quick summary of the latest release we made almost 2 months back. As I was telling, we are coming very close to the 2.1 alpha release. We couldn't just do it because of this mug. Either end of this week or the next week, we'll be trying to push that. So here we introduced a lot of these features, and similarly like the MVAPICH 2X supports not only the latest of MPI, but it also supports the latest of the UPC as well as the OpenSMAP. So if you take a look at the performance, so this performance chart actually shows not only like the evolution of the MPI stack from the MVAPICH side, but also combines that with the advances taking place in different adapters. So if you think of like these are the QLogic/Intel, the adapters, and then the Mellanox different kinds of adapter and the platform. So the very best these days we get is the Ivy Breeze together with the Connect IB, the Connect IB dual port FDR. So here you see like it's around like a 1 microsecond. So this is the small message latency, half of the round trip. So we are around like a 1 microsecond latency. And for large messages, of course, the bandwidth wins. So this is the Connect IB dual port FDR. So we get the best performance there. And if you see the unidirectional bandwidth, so this is the rate at which we are pumping data from one node to the other node. So we effectively get here like a 12.8 gigabytes per second, which is very close to 100 gigabits per second. And bidirectional is like 24.7. You multiply by 8, so it comes very close to 200. So these days with the commodity interconnects and using the MVAPICH stack and the Mellanox Connect IB dual port FDR, you should be able to really deploy 100 gigabits solutions for clusters. So not only we focus a lot on the internode, we also focus a lot on the intra-node communication, and this is here like it's trying to show like on Intel Ivy Breeze when two cores or two processes within the same socket are communicating. So we are able to give like 180 nanosecond communication latency for MPI send receive. So we continuously try to enhance in the intra-node design, and not only for the short messages, for large messages we have put these kernel modules. There are two kernel modules. Earlier we had the limit module, and many of the features have actually gone into the standard Linux distribution known as CMA or cross memory attach. So since the last release we have made that as a default. So any of the recent latest Linux kernel, you should be able to directly use that because that is the default, and you will get good performance in the bandwidth as well as for the bidirectional bandwidth for large messages. So we strongly encourage those kind of features to be used. Now we also have the MPI-3 Rma support. So this is the new one-sided feature. So here it shows like let's say put operation across the internode, get put latency. We can give you around like a 1.56 microsecond, and then the intra socket it is almost like a 80 nanoseconds, and then there is the bandwidth wise. Again, we can give you the full bandwidth here, and also the bandwidth whatever is available within the node. So it is a totally MPI-3 Rma is completely supported with all combinations of communication and synchronizations. There are almost like 28 combinations, and we have been able to support. So if you are an application scientist, you should be able to explore all those different kinds of communication and synchronization semantics and see whether you can really overlap computation with communication. So that is the goal of these MPI-3 Rma operations. So this shows an overview of the MVAPICH to X stack. So this is the unified runtime, which helps us to actually, at the network layer, unify the resources and the data structures for all these different programming models, not only for MPI, but also for the OpenSMEM and UPC. These are the representatives of the PGAS. And this we have been supporting since 1.9 version. So it gives you complete freedom to try with all different kinds of programming models, whether it's a very simple MPI OpenMP or pure OpenSMEM, pure UPC, or MPI plus OpenMP, or MPI OpenMP OpenSMEM, or MPI OpenMP UPC. So all those combinations you should be able to exploit. And that, so every time we make a release, we keep on updating not only the MPI version, the latest version, the OpenSMEM standard, also the UPC standard. So this stack actually gives you the complete freedom to try out all these different program models. So not only it allows to try them individually, you can also mix and match. And so this is where the hybrid MPI and PGAS programming field is going on. So think of like, let's say you have an HPC application and it is not scaling. So you may try to analyze and saying that which part is not scaling. Okay, it could be like some particular calls you are doing or some collectives that is not allowing you to scale. So if that is the case, then what you can do is actually, let's say there are two of these kernels, they are not scaling. You can try to explore saying if a PGAS implementation will help. And in that way, you can actually combine the benefits of both the MPI and the PGAS model. And this is actually the Exascale roadmap talks about this kind of newer paradigms to aim for the Exascale computing. So here I'll show you one example, like a Graph 500 we have taken. So this is what we did is in the Graph 500, the MPI programs, there are different MPI simple, then MPI CSC, CSR, there are different versions, and they were not scaling. So what we did is we tried to analyze, and then we saw that for some particular, like the routines, they were not scaling, so we took them out and put the OpenSMEM versions there. So then we had this hybrid version, MPI and OpenSMEM, and these numbers are actually taken from the Stampede. So if you see like with the 16,000 cores compared to the default MPI, you get almost like a factor of 13 improvement in this Graph 500, and similarly you can get very strong scalability and also the weak scalability. So that shows actually the power of this kind of a hybrid programming. So you can take the best of both the worlds and try to have your applications which will really scale as the system size is growing in a steady manner. So looking forward along this direction, as I said, like we already have the things ready. It is going through the final testing. So this is based on the very latest version, 3.1.2. We have the PMI2 based startup with Slurm, improved job startup. And yesterday in the tutorial, there were a lot of questions on Fortran support and all those things. So all these things are here. So might be we'll try to see later this week or early next week. You will see this release coming out. So then the bigger direction, what we are working recently very closely with NVIDIA and with Davide, who is sitting here. So this is the GPU Direct Rdma. We made a release just 2 days back. I'll show you some of the numbers. And broadly, not only we try to provide reduce the latency and push the bandwidth up, but now we have supported MPI3 Rma from the GPU buffers. So from GPU buffers, you should be able to do get, put all kinds of MPI3 operations, and we have optimized the collective support, excuse me, and also the point-to-point communication. And here it shows some numbers. So if you see, like this is the very traditional earlier MVAPICH 2, which is the CUDA-aware MPI, but this is before GDR or before GPU Direct technology came into picture. It was the small message latency, like from one GPU to other GPU, is the D2D latency was almost 20 microseconds. Earlier this year in the January, we reduced it to like that was the MVAPICH to GDR2OB. With the blue line, we are able to reduce it to around like a 6.5 and 7 microsecond. And this is the very latest what we released. Now you can see that it is 2.18 microseconds. So in 2 microseconds, you can actually take the data from this GPU buffer on one node to the GPU buffer on the other node. And of course, in this design, we are using a new library from Davide. I'm sure he will be talking today in his talk called a Gdr Copy Library, and that library is actually helping us to get this kind of performance. And not only in the latency, but if you see the small message bandwidth, Dan indicated like those medium message size kind of thing, that becomes very important. And here, if you see those 3 generations, without GDR versus with GDR, and then with the new GDR copy, we are able to almost improve it by a factor of 10 here, or compared to the last release by almost a factor of 2, the small message bandwidth, and also the bidirectional bandwidth, similar kind of things, we have improved by a factor of 2 here, and compared to the non-GDR, which is a factor of 10. So we also have the support like the MPI3 Rma support here. This is not completely optimized. We have some solutions where we can even reduce it later on. That will happen in the next release. But as of now, you can actually do MPI3 Rma operation with 2.88 microseconds. So the earlier I showed like two-sided is 2.18. So we give another 0.7 microsecond overhead for MPI3 put operation here, taking place from one GPU data from one GPU buffer to the data in the other GPU buffer. So this is the other application, the HUMD Blue. They indicated like Jens will be talking later on. He has a talk. He is the designer of this HUMD Blue. And all these numbers we got on the Wilks. Again, Filippo is sitting here. They were very kind enough to give us their system to put all these new libraries before even the release. We did a lot of experiments. So here we see like this is a strong scalability chart. We are able to get very good performance with the latest version. And also this is the weak scaling, around 2K particles per core. We are able to get very good numbers here. Now moving forward to the mic, Dan indicated the mic actually provides a lot of flexibility, but it also is very complex. So to optimize all these different paths, of course the offload mode is very simple, but once you go to the symmetric mode and then the native mode, all different communication paths come. And then the question is, okay, how do you really optimize? Not only at the point-to-point, but then you need to think about collectives, RMA, gradually up in the chain. So we have a complete MVAPICH to mic design supporting all these things. Of course, the offload mode is very simple, which the basic MVAPICH to supports. But all these, the other kind of intranode, the co-processor only mode, symmetric mode, native mode. So all these modes we have supported, and so this is again a good partnership with Dan, as he indicated. Like once the the Stampede was there, we were able to actually design, because all these stacks, you can design on 2 nodes or 4 nodes, but you really need to run on large-scale nodes to see whether it's scaling, even before the release. Otherwise, I mean, so you just push out a release, I mean, you never know, I mean, how it will perform. So that's how, for the GDR code, I mean, it has been very helpful to collaborate with University of Cambridge folks, and on the mic side, we are collaborating with the Stampede folks, so that when we push the code, the end users actually see that this code is really running on large-scale systems. So here it gives some performance, like this is the default MVAPICH 2 versus this is the MVAPICH 2 mic, like reduced latency, and you can see the significant bandwidth gain which you can get. And so not only currently it is running on the Stampede, as Dan indicated, but on 2 other systems it is running. The Blue is at the Virginia Tech, and the Beacon system at UTK. So these are all based on the 1.9 version, the same version running on Stampede versus all these other systems. And one big challenge which we see here, nothing to do with MPI. It's more challenges are with respect to MPSS. That is the stack from Intel. Every system deploys this MPSS stack in its own way. Okay. So that becomes a real big challenge. Like means even very simple identification of how do you identify mic, how do you identify host. I know Shanthan is smiling here, but that is a big challenge we see. That has nothing to do with MPI. So that needs to be resolved so that the community can really move forward with mic deployment. Otherwise, we'll always be in this kind of a mode. You put out a release, 5 people immediately come back saying I cannot install. Okay. So that needs to be resolved in the ecosystem. So currently we are working on a new version. This is based on the MVAPICH 2.0. This has like not only the active proxy support, passive proxy support, and also we have tried to optimize a lot of collectives. So we are hopeful like in another few weeks we should be able to push this out. So here it shows some kind of an example like how you can think of collectives, because the way these mic systems are, I mean, there are so many paths. So now you need to rethink how these collectives need to be designed, because it's no longer like a simple, if you think of binomial algorithms or some scatter reduce. I mean, those are the traditional algorithms, may not work well because when you go through the mic to host, as Dan indicated, the bandwidth is so low here. Reverse is more. So you need to come up with a total kind of new set of algorithms. And that's what we have done here. This is a paper we presented earlier in IPDPS. So here it shows like, let's say 32 node all gather, 16 host, 16 mic. So it's a 1,000 core experiment we are running. So this is the optimized, you can see, for even a 1K message size, we can reduce by 76%. Okay. And same thing like here, 8 host and 8 mic. This is a 512 core, so we can reduce by 58%. This is an all-to-all. This is the P3D performance. So unless you optimize all these collectives, it will be very hard for people to really run application in the symmetric mode or even the native mode. Offload mode is good. I think that will continue to give the good performance, but once you go into the symmetric and native, these kind of solutions need to be plugged in. Otherwise, at an application level, it will be very hard to exploit the performance. So in addition to this MPI stack, as I indicated, like we steadily go into this always like every year whenever some new features get added on. We started this Osu Micro Benchmarks in 2004, and keeps on like growing every time we introduce some, let's say, one-sided or RMA. Not only like we solve 2 things. Many times the end users even don't know. Let's say MPI 3 RMA has come. How do you really write MPI 3 RMA programs? So this is one way we try to introduce the users. So we give these code snippets in our micro benchmark, saying, okay, this is how you modify your, like write your application, let's say with the communication, synchronization, semantics. The same thing happened when CUDA things, with CUDA where MPI came, people didn't know like how to measure the D to D, device to device, or device to host, host to device. How do you do this GPU rank kind of things? We had a lot of discussion yesterday. So we enable the users through this kind of a benchmark so that they can actually start experimenting with it. And of course, in addition to that, it also helps to get these performance numbers and also validate your stacks, trying to see that, okay, your installation is good or not. And then this is widely used in the MPI community. And as I indicated yesterday, this also has become a part of a lot of procurement and the RFCs kind of things. And so we introduced also just together with the Gdr release, we had this Osu Micro Benchmarks 4.4. So the major thing we added here is the support for MPI3 RMA using the GPU buffers. And it also has not only MPI, it also has the OpenSMEM and then the UPC benchmarks. Now coming to the final part, this is related to the Chameleon project. We have been working on this for the last might be 1 year kind of thing. This is the new SR-IOV technology from Mellanox, which tries to provide the virtualization support. But many years back, I mean, in my group, we had done a lot of virtualization work, we called like a, just like you call OS bypass, that time we call like a gen bypass or a VM bypass kind of things. And that time the SR-IOV had not come, but we were able to still show that you can exploit high performance with virtualization. But now with the SR-IOV, things have changed. So here we are trying to show, let's say this is the MVAPICH 2 on basic SR-IOV to run, but then this is the optimized, this is the native InfiniBand, and this is the SR-IOV based solution, including all our optimizations. And here you can see that with we can have only 3 to 7% degradation in latency, or only 3 to 8% degradation in the bandwidth compared to native. Pure native InfiniBand versus virtualization based solution with InfiniBand. And this is trying to show some results like a NAS and Graph 500, similar kind of things. These 8 VMs across 4 nodes, so totally 64 cores we are using here. Similar kind of things, we see 3 to 9% limit. And this is the LAM-FPS application, 8 VM across 4 nodes, the similar kind of thing, 7 to 9% degradation. So the idea here is this Chameleon testbed, as Dan indicated, it will enable, this is a computer science, it is not a production environment. People should be able to run experiments on these kind of systems, trying to carry out research on virtualization or use virtualization for their applications. Okay, all kinds of experiments people should be able to run here, and our plan is to have, we'll have a MVAPICH 2V, that is the MVAPICH 2 virtualization. That will be the stack which will be coming out, which will be deployed on the Chameleon testbed, and then people should be able to experiment with the virtualized environment. So looking forward, so this is our overall plans in future. We have been continuously working on this new dynamically connected transport, or DCT, from Mellanox. So that is coming as a new transport mechanism, as an alternative to RC and UD, to give very good performance and memory scalability, hybrid programming, continuous directions in the GPU support and accelerators, this collective offload framework, CodeDirect. We had a lot of questions yesterday in the tutorial session about this, extended RMA support, the topology of our collectives, power our collectives, and this new MPI tools interface that we have enabled in the MPI 2.0, but it is just like taking the data, but we will try to also enable the control side so that people can actually play with MPI stack. And then, of course, the extended checkpoint restart and migration support, and low overhead and high performance virtualization support. So all those are in our roadmap, and as we keep on working on some of these solutions, you will see these solutions will be pushed out into our releases, so the community can actually take advantage of these to carry out their research. So with this, let me close here.